I would like to kick off today's program from that very point. I have received over 150 emails, plus, many emails from the senior 4 students, of course, but around 150 to 200 giving me feedback on what we have been, on the assignment that I had left on the Archimedes principle. And many people have suggested that I try and go through the numbers which I had left with them on Archimedes principle and the law of flotation, around like 3 numbers, which almost everyone was citing, that at least I should use the opportunity when people still have access to the TV before we go back to school, and then we try and see how their solutions come about. So today, I'm here to go through that assignment, and I've already thanked those people who have tried it out. I know very many people have tried it, very many people have succeeded. Of course, some have had a bit of challenges here and there, of which we have gone about them. However, the assignment which I'm referring to was on Archimedes principle, which I picked from the reference book for our level. That was ordinary level physics. About I shared with very many people through my email this set of questions. Everyone who was sending me an email requesting for them, I was still sending them. And I understand that there are very many people who have shared them. I'm glad to know that people down there in regions of Soroti, there is one individual or 3 who have access to the internet. And I'm being told that each time this person sends me an email and I send them the work, they take an initiative to go on and even share with the other students in the community. Thank you very much. I think the name is Ebo. I'm forgetting the other name. Yeah, but the student is called Ebo. He's in Soroti. Thank you for that job well done. Each time he receives the assignment, he downloads it from his phone. I don't know, maybe the PC. He goes on and shares with other students. He shares with around 15 to 20 of them. So that is very good. Now, among the numbers which I had given, of course, very many people managed to do number 1, number 2, number 3, number 4. But most of the queries were coming from question 8, which I'm going to, of course, write down here. This question was reading that a piece of marble of weight 14 newtons and relative density 2.8 is supported by a light string from a spring balance and lowered into a vessel of water standing on a weighing machine, full stop. So the question goes on to say that before the stone enters the water, the weighing machine reads 57.5 newtons, full stop. What will be the reading of both spring balance and weighing machine when the marble is completely immersed in the water? So this is this was question 8 from that revision exercise, and it is among the numbers which were giving people some little bit of difficulty. But of course, some managed to do it. A piece of marble of weight 14 newtons. So I've been given the weight in air, which was 14 newtons, a relative density of the marble, 2.8, is supported by a light string from a spring balance and lowered into a vessel of water standing on a weighing machine. Now, before the stone enters the water, the weighing machine reads 57.5 newtons. What will be the reading of both spring balance and weighing machine when the marble is completely immersed in water? Now, first of all, what we need to know is that if this is weighing 14 newtons, then it means that when the marble is tied on a light string, the word light is trying to communicate that the weight of the string is almost negligible. So the spring balance will read 14 newtons. May imagine something like this. So the reading of the spring balance here is the weight of this in air, which is now 14 newtons. Then, on the other side here, we have a weighing machine. I'm going to try and model a digital type of it. That maybe it's what we're talking about. That's its pan. So on here, we have maybe a vessel, but then this vessel contains water. So the reading of the weighing machine initially, which is 57.5 newtons, is the weight of the vessel and the water inside it. Then, when they bring the marble and they lower it inside, of course, while still connected to the spring balance, the question is, what will this read and what will this read? Now, we need to understand one thing. Fully immersing the marble into the vessel containing water is going to cause its weight to change. Why? Because of the upthrust force that will try to act on it downwards, therefore reducing its resultant weight from what it was before when it was in air or in space. So, when the marble is immersed into the beaker, the spring balance will be reading its apparent weight. And we say that that apparent weight will indeed be the upthrust. However, the weighing machine will now be reading the original weight plus the apparent weight of the marble. So this is what we're saying. that new spring balance reading is the apparent weight. Of the marble. Remember, according to Archimedes' principle, we say that when a body is wholly or partially immersed in a fluid, it experiences an upthrust, which is equal to the weight of the fluid displaced. Now, how am I going to find the apparent weight? Apparent weight, yeah, of the marble. Written weight twice. Now, how am I going to find this apparent weight? I'm going to use Archimedes' principle, but according to Archimedes' principle, we say that upthrust is apparent loss in weight and it is also equal to weight of the fluid displaced. Okay, in this case, of the water displaced. Now, I want to base on U weight in air minus weight in liquid, of which this is the apparent weight of the marble, and say that this will be the weight in air minus the upthrust. Now, I know the weight in air. I don't know the upthrust. I've been given the relative density. So the relative density is going to help me determine the density of the marble, because by definition, that is the ratio of the density of the marble to the density of water. Then if I know the density of the marble, it means that I can use the definition of weight as mass times acceleration due to gravity, and then I bring in mass as density times volume, from which I can know the volume of the marble. Then after knowing the volume of the marble, it means that now I can go on and find the volume of the water that will be displaced, which is contributing to this upthrust, from which I can know the weight of the water displaced. And then after knowing the weight of the water displaced, it means when I substitute for it here, because it will be equal to the upthrust, I'll be in position to know the weight of the marble in the liquid, which will be the new spring balance reading. It's indeed kind of a technical question, but it's good as an assignment. Why? It is testing all the knowledge that we acquired about Archimedes' principle. Because, number one, they're trying to check, do you remember or did you understand during our discussion that when the spring balance, when the mass tied on the spring balance is lowered into a beaker containing water, then the reading of the spring balance is the weight of the body while immersed in the liquid. That is step one. Because that knowledge is what helps us make this interpretation, that what is the new spring balance reading. Remember, the new spring balance reading is the reading of the spring balance when the marble is immersed in the vessel containing water. Then step two, knowing that in order for us to find this apparent weight of the marble, we must quote the definition of upthrust, which is apparent loss in weight, but that alone will only bring us to this point. But then there's a question of what is the upthrust. So we again refer to upthrust as being the weight of the water displaced. But now there is also another challenge. We don't know the weight of the water displaced. But since we know the weight of the marble, of which the marble is being fully immersed in the vessel, then it means that using the definition of mass as density times volume, I can go on and play around with the weight, which will give me the volume of the marble. And then since this was fully immersed, it will be equal to the volume of the water displaced. So it's a very good question. And I'm going to walk through it very slowly and with a lot of care. Now, I know this. This is what I don't know. But we're saying that upthrust is weight of water displaced from the vessel. So this is the density of the water times the volume of the water times G. Now, I know the volume of the water, we know G. Now, our challenge is on this. What is the volume of the water displaced? And we're saying that however, the volume of the water displaced is equal to the volume of the marble. Of which the weight in air is mg, which is density of the marble, volume of the marble times G. Since I know the relative density of the marble, I really hope that my learners out there are following me through. Relative density will be density of the marble over density of water, such that the density of the marble is now going to become the 2.8 times 1,000, which will now give me 280 kilograms per meter cubed. So this one I also know from this definition. It's a question which is testing us on all that physics around measurements, Archimedes' principle, and the law of flotation. So, I have my weight in air as 14 newtons. So it means that 14 is equivalent to 2800 multiplied with volume of the marble multiplied with 10, acceleration due to gravity, and then the volume of the marble is going to become 14 divided by 28,000,123. So this is 1 over 2,000. So this is the volume in meters cubed. Now this is the volume of the marble, but it will also be equal to the volume of the water displaced. Hence, volume of water displaced will be 1 out of 2. Now, I'm going to bring this and I substitute it here so that I can find the upthrust. Upthrust is now going to become density of water, 1,000, volume of the water displaced, 1 over 2,000, times acceleration due to gravity, which is 10. So this, that, with that, I'm seeing around 5 newtons. So that is the upthrust that is experienced by a marble of weight 14 newtons, relative density 2.8 newtons, when wholly immersed in water. Therefore, equation star will now become the weight of the marble in the liquid as the weight in air, 14 newtons, minus the upthrust, which is 5, and that will give me around 9 newtons. Yes. So that is around 9 newtons. And this is also the new spring balance reading. So I'm going to deduce that new spring balance reading is the 9 newtons. So basically, that is what was being tested there. Of course, it seems a little bit wordy, but it's a very good number for practice. Why? I was congratulating all those people and indeed instilling a lot of confidence in them who managed to interpret this question and arrived at this solution. Why? Because it requires somebody who has really understood that physics of Form 1, measurements, and then also the knowledge of Archimedes' principle in order for you to do this number. And it's also testing general knowledge. How? On the second part, they're saying, what will be the reading of the weighing machine? We are finished knowing the reading of the spring balance, but now we also have this other challenge. What is the reading of the weighing machine? Now, definitely, if this, when immersed here, according to Archimedes' principle, will not seem to weigh 14 newtons again, then it means that the reading of the weighing machine will be the initial reading plus what this apparently weighs when immersed in the water. So, reading of the weighing machine we're saying that this is the 57.5, which was the initial reading. I think it was 57.5, yes? Yeah, 57.5 plus the 5, plus I called 5 newtons the upthrust, which is the weight of the water displaced. Then I have 57.5 plus 5. This gives me 62.5 newtons. Now, upthrust, apparent loss in weight of an object. And indeed, we saw during the procedures for verifying the Archimedes principle that when we immerse a body into the overflow can, the weight of the water that was displaced is equal to the upthrust experienced by the object which we have immersed in it. Now, what does that mean? It means that in an event that this, the overflow can, did not spill out any water, then whatever would have spilled out, or whatever that is being displaced, for example, in this example, is still remaining inside the what? The vessel. And remember that this one is not seated on the weighing scale. Oh, I need to make this very clear and indeed clarify on it. I want to explain this again because I think I was using the wrong words at first. The reading of the weighing scale is going to be the initial reading of the weighing scale, of which that was the weight of the vessel plus the water, which was mentioned in the question as 57.5 newtons, plus the apparent loss in weight of this, or plus the weight of the water that will be displaced as a result of this being lowered into, of this being fully immersed into the vessel, which is now the what? The upthrust. So 57.5 newtons plus the 5 newtons gives us 62.5 newtons. So it's a bit a technical question, but if you really understood that knowledge around their measurements and Archimedes' principle, then you would be in position to do this and in a successful way. Now, the other last question, which I want to share with you, was number 13. I hope that people have written this down. They're just questions which require basic understanding of the subject content in that topic. This one was reading that a light spiral or helical spring which obeys Hooke's law has an unstretched length of 220 millimeters, full stop. It is attached at its upper end to a fixed support and when a piece of metal of mass 2 kilograms is hung from the lower end, comma, the spring extends to a length of 274 millimeters. Now, this question had a combination of Hooke's law and Archimedes' principle. Find the force in newtons needed to produce an extension of 10 millimeters. Now I'm going to write one question and then give a solution. So they are telling us that original length, L naught, is 220 millimeters. It is attached at its upper end to a fixed support, and when a piece of metal of mass 2 kilograms, so the mass M1 is 2 kilograms, contributing to a force F1 of 20 newtons, using the fact that force is mass times acceleration due to gravity. So this is 2 times 10, which will give me that force. From the lower end, the spring extends to a new length. So new length L1 is 274 millimeters, which means the extension E1 will be 274 minus 220, which will translate to 54 millimeters. Find the force in newtons needed to produce an extension of 10 millimeters. Now the question is, what force will produce an extension of 10 millimeters? So that is the basic application of F is equal to KE, which is Hooke's law. Hooke's law, that one we talk about when we're doing that section of mechanical properties. And just to remind you, Robert Hooke made discoveries on elastic materials, and he came to a conclusion that the force applied on any elastic material is directly proportional to the extension produced in it, provided the elastic limit is not exceeded. So it is very clear here that we are dealing with a spring which obeys that law. And if a spring obeys that law, then it means that using Hooke's law, F1 is a constant E1, F2 is a constant E2. This is equation 1, this is equation 2. This usually leads us to that famous equation of ours, that F1 out of F2 will be E1 out of E2. So F1 I have as 20, F2 is unknown, E1 is 54, E2 is 10. Now, you don't need to hustle with converting these to meters. Why? Because we're seeing that our generalization of the Hooke's law to do with such kind of word problems brings us to a ratio of 2 forces and a ratio of 2 extensions. So if these are of uniform units, they will cancel out. That's why I kept the millimeters. So it brings me to a conclusion that F2 will therefore be 200 divided by 54. When you cross multiply and then make F2 the subject. So I'm having a force of around 3.7 newtons. So that was part A. Then the second part was asking, when the metal is totally immersed, so this was basic application of Hooke's law. Now we're going to Archimedes' principle. I usually tell people not to go by most of other people's words who keep claiming the Abbott is too advanced, numbers are so complicated. It's thank God that I've gotten the opportunity to do some numbers with you here from that book. So the next time that you go back to school, kindly do not fear the book. In fact, it's our reference book at the ordinary level. There is no way they can choose a reference which is not meant for us. Numbers there are so much doable, only that sometimes they require some extended thinking, of which it's also proper training for us. So they're saying that when the metal is totally immersed in water, comma, the length of the spring becomes 247 millimeters, full stop. What is the upthrust of the water on the metal? So what is the upthrust of the water on the metal? So we know that by definition, upthrust is weight of the water displaced. Yes. They are giving us the new extension of the spring balance at its upper end at a fixed support, and when a piece of metal of mass 2 kilograms is hung from the lower end, the spring extends to that. Now they're saying when the metal is totally immersed in water, the length of the spring becomes that. Now, this statement here is going to help me find the weight of the metal when immersed in the water. Then after finding the weight of the metal when immersed in water, in order for me to find the upthrust of the water, I'm going to use the fact that upthrust is also apparent loss in weight of the metal, of which I know its weight in air, because it's what I calculated first here as F1, then that will give me the solution to this. So, using Hooke's law first, I'm going to say that F1 out of F1 out of F3 is equal to E1 out of E3. Now I'm calling this a third force. Why? Because I'm dealing with another extension. This was my second force. Then, yeah, let me call this E3, my third extension. So this is going to translate into E1, I have E1 somewhere here. 20 out of F3 being E1, which is 54, divided by E3. Now E3 will be 247 minus original length 220, and I think that will be 27. Yeah, that will be 27 millimeters. So this is 54 divided by 27. So F3, such that F3 will now become 20 times 27 divided by 54. Let's see what we get. I have 20 multiplied with 27, 540 divided by 54, that gives me 10. So F3 is now 10 newtons. But that 10 newtons is weight of the metal in water. It is the 10 newtons. So, by definition, upthrust will be weight of the metal in air minus its weight in water, and this will be 20 minus 10, giving me 10 newtons. So that is the upthrust that I will get as a result of lowering the spring balance, the metal tied on a spring balance into water. Then, part C was asking us to find the mass of water displaced by the metal. find the mass of water displaced by the metal. Remember, I've gone back to ensure that I clear the space as far as Archimedes' principle and the law of flotation is concerned. Through that assignment, which I shared with very many of you through my email, people tried doing, and then they forwarded their solutions, went through them, and majority of them, after seeing the solution to those two numbers, they were claiming that I should try and go through this exercise. But because of time, I've only picked out these two numbers, which were challenging to many of us who tried them out. So find the mass of water displaced by the metal. Remember, I know the upthrust. I know the weight of water displaced, because that is the upthrust by definition, or according to Archimedes' principle. Weight of water displaced is 10 newtons, and this will also be m times g. So the mass of water displaced is 10 divided by 10, which will just be 1 kilogram. Basically, that is 1 kilogram. Now, the last part was asking us to calculate the volume of the piece of the metal. Calculate the volume of the piece of the metal. Now, finding the volume of the piece of the metal is really going to be a piece of cake. Why? From the definition of density being mass over volume, it means that the volume is the mass divided by the density. Now, I can know the density of this piece of metal. Why? If I know the weight of the water that it has displaced, then it means that I can know the volume of the water that it has displaced, of which the volume of the water that it has displaced is in fact equal to the volume of the metal. Oh, let's quickly go through that. Calculate the volume of the piece of the metal, yeah. Now, since the metal was wholly immersed in the water, then the volume of the metal is equal to the volume of the water that was displaced. And this will be the mass of the water displaced divided by the density of water. I'm quoting this from the fact that density is mass over volume. So when you make mass the subject, volume the subject, then this comes up, then this goes down. So I know the mass of the water displaced, that is 1. I'm going to use the definition of, the known constant for the density of water as 1,000. And then this will translate into 1 exponent minus 3, or 0.001 kilograms per meter cubed. That is the volume of the metal. Oh, I've started units of density. This is just meters cubed. So, the people who did not get a chance to mail me and have a look at these numbers, kindly reach out to me on my email. I share with you those questions, lutherken@gmail.com. You have a look at them. There were around 13 numbers, and I've just tried to have a discussion with you on the most challenging according to the feedback which I was getting from those who tried them. Otherwise, because of time, I will not be in position to do question 3 there, but it was also a good one, though it was very easy to interpret because we had already done examples on that. Question 3 was to do with the ferry, given cross-sectional area in the region of its waterline, then adding 16 cars of average mass, 1,100, and then they're asking us to find the extra depth to which the boat will sink in the water. This one, because of time, I may not be in position to share with you, but I know that at least many people have tried to do this. They managed to do this. Maybe also people who have the book, Abbott, you should also do you should also look at the examples which were worked out there in the book itself. Otherwise, I would like to applaud all those people who went under the bed, who checked in their would-be trash at home, looked for the Abbott, picked it up, and have already started doing some of these numbers. I think there is a one Chisitu from Namiryango who emailed me and even showed me a copy of his Abbott, claiming that from the time when the parents bought it, he had never used it again in Form 1 until when he started interacting with us here and indeed discovered that the book was useful, and many others. But it was so interesting. People have the books, but they're not even using them. So please, do the needful. We are resuming anytime next week, and I hope that you're all prepared to go back to business as usual. Otherwise, I would like to wish you the very best of the remaining part of today, and until next time, I sign out.
Osomeseza omwana wo mu masomero ga Giant Schools omuli kampasi y'Ebombo Kalule n'ey'e Kabalagala tobona bweraliikirivu bwonna olw'omusingi okutambuzibwa ebyenjigiriza n'ensoma y'abayizi ey'omulembe. Mu masomero gaffe gano gonna tusomesa arts ne sciences okuviira ddala ku siniya esooka okutuuka ku siniya ey'omukaaga, nga tusomesa abaana okuviira ddala ku mutendero gwa kindergarten okutuuka ku kibiina eky'omusanvu. Tulina abasomesa abakugu mu kubangula abaana n'okubateekateeka. Ebibiina abaana mwe basomera eby'omulembe omuli buli kimu ekikwata ku ebyo bye basoma, ebisuula ebyazimbibwa obulungi, ebigazi ate nga biyonjo, okumanya ebisingawo tukubire ku